Question here gets a little harder now that we've got a horizontal component as well as a vertical component of the motion. So let's start with our summary step here. Here's the ground level here. This arrow is fired with an initial velocity. It's going to follow a parabola. Ultimately, we're trying to find out what the range is. So in other words, what the distance is it travels before it hits the ground again. But before we do that, we need to resolve it into its x and y components. So we know that u is 45 meters per second at an angle of 40 degrees above the horizontal. And so part A asks us to calculate ux and uy. Well, if we think about that just in terms of our right angle triangle, this is going to be uy, the vertical component of the motion. That's going to be ux, and this is u. So we can pretty simply see from that uy equals u sine whatever this angle is here, and ux equals u cos theta. So we can bear those things in mind very easily to do part A and simply substitute in those. So uy is going to be equal to 45, uy is going to be sine of 40 degrees, and ux is going to be 45 cos of 40 degrees. And if we just grab our calculator and calculate those things out, so we've got 45 times sine of 40 gives us, let's call that 28.9, 28.9. And if we go 45 times the cos of 40 degrees, we get 34.5, let's call that 34.5 meters per second for each of those. And so that means it's got a vertical component of its velocity. So what we can say is that uy equals 28.9 meters a second and ux equals 34 equals 34.5 meters per second. Okay, so now we're in a position to work out what the range of this arrow is going to be. And it'll be in the air for as long as it's in the air. It's going to hit the ground when it hits the ground. In other words, it's going to hit the ground when it gets back at the start. So what we can do is we can work out the flight time. We can work out the time to the top of flight like we did before. So if we consider this as the time to the top of flight, so v, and we're just considering the y component only, uy plus, well, it's gravity times time. We've already considered the up direction to be our positive direction because it's 45 degrees. Up and to the right are the positive directions in our motion here. So that means that g is going to be minus 9.8. So v minus u equals gt, just like we did before. T is going to be v minus u divided by g, which is going to be 0, the velocity, the y component of the velocity at the top of the flight, minus the initial y component over minus 9.8, because we're considering downwards as negative. And so that's going to be 0 minus 28.9 divided by minus 9.8. So our time to the top of a flight is going to be 0 minus 9 divided by 9.8, and it's negative 9.8. It's going to give us a time of 2.9, give us a time, sorry, of 2.9 seconds to the top of flight, okay? So that's the time to the top of flight. Let's put that away for now because we've used that one. Now that we've got the time to the top of flight, we can quite simply say that's the time to the top of flight. Then the time for the total flight time is going to be equal to 2 times 2.9, which is going to be 5.8 seconds to the top of for the total flight time. Now we know the time that's going to be in the air. We can calculate the range of the arrow very, very easily. So the distance that we're going to travel in the x component is simply going to be the velocity in the x component times the time. Now that just comes from the basic idea that speed is distance over time, or that my velocity in the x component is the x component divided by time. So that's where that's come from very simply. And of course, The horizontal component of the motion doesn't change. The velocity doesn't change, and so we don't need to worry about that changing over time. All right, so we can then just put that in. It's going to be UX 34.5 times the total flight time, which is 5.8 seconds. Multiply that is going to give us just around about 200 meters for our total range.